Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. With today's show, we conclude our TensorFlow Dev Summit series, which was recorded on location during the summit a few weeks back. This interview features my conversation with Alfredo Luque, a software engineer on the machine learning infrastructure team at Airbnb. If you're among the many TWiML fans interested in AI platforms and machine learning infrastructure, you probably remember my interview with Alfredo's colleague, Airbnb's Atul Kale, in which we discussed their Big Head platform. In my conversation with Alfredo, we dig a bit deeper into Big Head support for TensorFlow, discuss a recent image categorization challenge they solved with the framework, and explore what the new 2.0 release means for their users. If you're interested in topics like these, TensorFlow, deep learning, you'll probably also be interested in the awesome swag box that Google gave out to Summit attendees. They included their new Coral Edge TPU device and the SparkFun Edge development board, as well as some other really cool goodies. And I'm excited to give you an opportunity to win one in our latest giveaway. To enter, just visit twimlai.com/TF giveaway and let us know what you would do with this kit if you got your hands on it. We'd like to send a huge thanks to the TensorFlow team for helping us bring you this podcast series and giveaway. With all the great announcements coming out of the Dev Summit, including the 2.0 alpha, you should definitely check out the latest and greatest over at tensorflow.org, where you can also download and of course start building with the framework. And now, on to the show. All right, everyone, I am here at the TensorFlow Developer Summit with Alfredo Luque. Alfredo is a software engineer at Airbnb. Alfredo, welcome to This Week in Machine Learning and AI.
Hi there.
Let's get started by having you share a little bit about your background and how you came to work in machine learning and AI, and in particular on machine learning platforms and frameworks.
Sure. So I guess my interest in machine learning started in college, actually, well before, there were a lot of applications to do this. Started with writing some of my own kernels for GPUs by hand, and exploring some of the really primitive ways we could do ML back then. Since then, a lot of things have changed. I mean, since the last 5 or 6 years, we had a lot of new developments.
What interest drove you to write your own kernels?
I was just very curious about what could be done there. There had been a lot of interesting and promising research around image recognition. Mm-hmm. First, the convolutional neural net papers have been starting to drop, and there was a lot of really great applications to actually try this out yourself outside of a research setting. So that's what really got me into it first. I went on to work in online advertising, real-time bidding, and later to work on my own hedge fund. And there we really leveraged a lot of techniques in natural language processing, which further kind of drove me into the field.
Okay.
Yeah.
Oh, interesting. I don't think I've talked to someone that started their own hedge fund before.
Yeah.
So you're at Airbnb now. What's your focus at Airbnb?
So at Airbnb, I work on our machine learning infrastructure team. You actually had our engineering manager on here a couple of episodes ago. Basically, we build tooling to make machine learning really easy. Developing models and productionalizing them should be something that everybody can do, is kind of our belief. Mm-hmm. And I specifically focus on aspects involving the actual creation of models, actually developing which techniques you're going to be using, making sure that it's really easy to assemble those things, and making sure there's no additional difficulty in actually making it production ready. So we have our own libraries that wrap around most of the major ML frameworks and make this a really, really easy thing to do. Mm-hmm. So TensorFlow is one of those, but we support most of the major ML frameworks.
Yeah, that was one of the aspects of what you're doing with Big Head that struck me in that initial conversation with Atul. The extent to which you've invested in
building the platform to be framework agnostic and supporting, many different frameworks that the data scientists and software engineers want to use. Is that, since that responsibility falls on you among others, but how do you kind of manage the burden of doing that?
Yeah, so we kind of dove in head first is the answer. There are really two approaches that you see to handling this sort of agnostic behavior. One of them is you basically treat a machine learning model like a black box, right? There is some interface, you feed it some data, and it's going to spit something out, and then you don't really care what happens inside. And that definitely does make your platform pretty agnostic, but it also means you don't really have a really nice integration. So as a data scientist or an ML engineer, if I'm actually trying to develop a model, it becomes much more difficult if all I hand off is just this big black box. We don't know if it's going to run efficiently. We don't know if I run it in a different environment, it's going to behave the same way. And I'm not really developing using the same tooling that's actually going to be running my model. So major ML frameworks have started really working on this issue of integrating everything nicely. I think in 2.0, TensorFlow is really making strides there. And there's other frameworks as well that has really started focusing on this. But our goal was to really build these libraries that cleanly wrap around the major features of each framework. That does mean a high support load, but it also does mean that our users, when they write something, really feel like they're interacting directly with the framework and can use all its features. And when they go to productionalize their model, then they get exactly what they wrote. And they have a lot of predictability. And more importantly, they can just swap out TensorFlow for XGBoost or something else and get the exact same results in the earlier parts of their pre-processing. So that was a really important aspect of Big Head for us, was working on that.
I would imagine that swapability kind of forced you down an approach other than the one you've taken, where it's more black boxy, more kind of least common denominator. How do you expose the full functionality, but yet still allow people to do swap outs?
We basically dive into the internals of each framework. And, and try to find the interface point that sort of makes sense to let users develop their model, but then encapsulate it in a way where we know how to now feed data into that model. So once we really establish the method by which we can feed data into a model of a given framework, then whatever is on the other side, we already know how to deal with, essentially what's in the model. And what comes before, we built ourselves, or the user wrote. So we have a really, really good way of essentially converting all these data types and making sure the flow of the data works well. Another aspect we're exploring as well is once you write what we call a big head pipeline, essentially your entire workflow graph of all the pre-processing steps in your machine learning models, we can actually potentially convert that into, if you're using one framework, that framework's native operations. So if you're using purely TensorFlow, you can compile it into a TensorFlow graph. And I think this approach is neat because in that case, you'd get basically no loss in performance. But again, it does require diving down into the internals of each framework. And I mean, that is a lot of work, but we think it's worth it. We've also been collaborating directly, looking to, as we open source, integrate engineers from those different platforms and supporting some of these wrappers and contributing directly. So,
one of the things that was featured here at the summit was a case study video about a project at Airbnb focused on categorizing listing images. What's that project about?
Yeah, so at Airbnb, we have a lot of listing images. Basically, every listing you see might have between 5, 10, maybe more images. And one of the challenges is showing the relevant images, right? So when you go try to book an Airbnb, typically the first thing you want to see is, picture of the living room or the bedroom, and not like the bathroom mirror, right? So it becomes really important to get accurate classification of those images so that we can choose what to present. And for hosts, we can also assist them potentially in reordering them. So It was a pretty big project because while image classification is a well-known solved problem, the issue is the scale. We have almost 500 million images to sift through. And if you try out a new model and you want to backfill it, that's a lot of time to backfill it. So some traditional approaches, just kind of running this on there's things like Spark, you can run this on just with CPUs, would have taken months with any framework. And so one of the things we did was really focus on optimizing that. And just taking a pre-trained model on Keras, with some of the optimizations we made earlier in the pre-processing, we were able to get that to a few days, just running on a few machines with GPUs. And so that was a pretty big one for us. And there are many other projects like this that can use a similar approach.
What was it specifically that allowed you to get that to a few days from weeks or months?
Yeah, so I mean, when you have image data, unfortunately, it's never exactly in the format that you need. In an ideal world, you have perfectly resized data set, everything's like nice and clean, but we have some images that might just they might be corrupted. They're the wrong size. If you're using something like ResNet 50, I mean, you have to do some scaling and kind of normalize the values.
224 by 224 image.
Yeah, and then normalize it to a 0-1 range and reorder the color channels. A lot of this stuff was written in Python, especially if you use Keras. There's a lot of Python in there.
Right.
And that becomes very, very slow.
Okay.
That ultimately limits, even if you have the fastest GPUs out there, they can't get images quickly enough to actually run inference on your model.
Is the primary time savings inference focused, or is it the training?
In inference.
Okay.
And actually at Airbnb, most of our scaling issues are always with inference and rarely training.
Okay.
We found at least that typically with the Volta GPUs or fused TPUs, a couple of machines are plenty to reasonably train whatever you have. But for inference, that's the real key. If you try to backfill something
all day,
new,
every day at huge scale.
Yeah, and if you try out something new, every day you get more images. So now it's going to take even longer to backfill all of history. So we find ourselves backfilling all of history a lot, basically every time we try out something new.
Yeah, let's dig into that particular point a little bit more. This was something that I don't recall if Atul and I went really deep into this, but Airbnb has spent a lot of time, like backfilling is a big part of the way you think about the problems that you're solving, and like Zipline, a big part of what it's doing is trying to manage these point in time features and backfills and walk us through like that whole space. Is backfilling and where does it arise in your workflows?
Yeah, so a really simple definition of backfilling would be, if you have data that's collected every day, and saved every day, then, we might train our model on a couple of days. But if we want to apply our model to all the data that we've ever collected, we have to go through all of history. So it might have started being collected 2 or 3 years ago.
So what's a specific example where you might want to apply the model to all of history?
So that project is actually a great example. So
it's categorizing the listing images. Okay.
Yeah, so if you just categorize last month, it's not too useful because, frankly, the user could click on a listing that hasn't been categorized, right? Doing that in real time ends up being a lot of wasted effort because Airbnb has a limited number of listings. It has many, but it's a finite number, and it's a pretty manageable number. And many users will be viewing the same listing. So you have a lot of duplicated work there, and it's a pretty expensive computation to go through 15 images every time somebody clicks on it, right?
Okay.
So if we want to categorize these images, we need to do it for all listings, right?
Got it.
And if you want to run an experiment then and see, by providing these better labels and these reordered images on the sites, do we have a revenue increase? You really need to go through everything.
Okay.
So that's kind of a rationale for it.
And so it's again, backfilling does it only occur in inference scenarios, or is it also relevant to training scenarios?
It could be relevant to training scenarios if you need to generate training data. So one example of this is there are models that use embeddings. So essentially, instead of a single value, you're outputting a chunk of your network, right? Many of these models do need these embeddings, and so you have to go run the embeddings model on all your data. If that embeddings model changes or something downstream changes, you might need to backfill everything.
Okay.
So there are scenarios like this where for training you might need to backfill something. I'd say the majority are inference. And for most enterprises, it's pretty similar to what we've heard as well. It's inference where we need to chuck through a lot of data.
Right.
Yeah.
Right. You kind of set up this backfill process. Well, the big task was to reduce the amount of time it took to categorize these images so that when you're doing the actual backfilling, it's a manageable time. You mentioned kind of a big part of what you do is like digging deep into these frameworks. To what extent was that required in this project?
Yeah, so we had actually done that work already in this case
Okay.
for essentially wrapping Keras. And
Right.
There are different backends for it, but we had specifically also wrapped TensorFlow specific implementation. The investment here was also largely in building these reusable primitives that we could use whether we were using TensorFlow or not for pre-processing these images. And we believe this time investment was largely worth it because we have many other models leveraging these things now. And it did enable our data scientists to experiment using a variety of models, and they would always get the exact same data set after pre-processing. So we actually ended up writing a lot of these things in C++, largely because we wanted to use, this is getting a little into the weeds, but we wanted to use CPUs for this pre-processing because the models then can use all the remaining GPUs. And this provided a pretty significant performance boost. And it also meant that anything else, like a tree model, could leverage it. So that was kind of the rationale for investing the time there and digging in. And so far as Keras is concerned, the investment there was really making multi-GPU inference very easy. Our users don't have to think about these things. Essentially, whatever machine you're running on, we figure out what's on there, configure your model to run in an optimized fashion. And that's one thing I think framework authors are starting to really focus on is you don't need to think so much about the low-level mechanics of how you're running it.
I'm trying to think of like if you're kind of starting out here and you're trying to, say you've got a team that you are supporting and you've got folks that want to work in different frameworks. Like, where do you start, or where would you start if you were starting all over again in like providing them some tooling that would allow them to be most efficient? Where do you think like the most value is in the kind of things that you've been working on?
I think about this a lot, but I think we've made more or less the right calls. There are two areas that we really identified where people waste a lot of time. One of those is simply generating your features to train on and to use for inference. This is a huge time waster because oftentimes it means a lot of really, really hacky querying of a database. You have no guarantees of point-in-time correctness or anything. But if you do want to guarantee that, it ends up being a lot of work. And typically, when you're building a model, you're going to iterate through a lot of different data sets, a lot of different variations of features. So that was one really, really huge area where people were wasting time.
And this is basically been productized at Airbnb and Zipline.
Yeah, that's Zipline.
Right.
Yeah. We like to call it the engineers working on it call it a time machine for your data warehouse. And
so actually, let's remember the second one, and let's just dig into this, because I think as I've kind of studied what you've done with Zipline, I mostly get it, but like the point in time correctness, I don't feel like I fully get exactly the situations where you need that. And so maybe walk through kind of where that, the various places that comes up and why it's important and how you get there.
Yeah, there's a lot of models that, for instance, will use aggregations, right? Or some metric that's calculated every minute or every hour or even every day, right? But the problem is how a data warehouse works is often at midnight, you start feeding in data. And, at the other midnight, you basically cut it off. And there may have been updates in that window that you miss. There may be things that happen afterwards that actually belong to that day. There are a lot of things that can go wrong, and technically your data is not perfectly accurate, right? Zipline actually worries about the mutations that happen to a database, and it will actually look at, for a given window of time, for a given aggregation, how do I do this correctly so that the numbers I give you for your model are reproducible and they're perfectly accurate. So this reproducibility is really, really key. I think that's, for somebody building a model, one of the more interesting aspects. If I'm going to get the same data later on in time or earlier on in time, I know I'm always going to get the same thing. And that really just gives you a lot of ease of mind.
So what's a specific example of a model that needs this kind of point in time correctness?
Yeah, so I can't get too in the specifics, but for many of the fraud models, you really do care about actions that a user, for instance, may have taken during a certain window of time. And those windows can get very, very granular. So if you're off, or if you're missing data, or even worse, if during pulling the data 2 consecutive times you get different results, that's really going to throw off your model. And the consequences there can be pretty disastrous. So you really care about the precision. That's one case where you might have very, very granular time windows, and it's very likely that you'll miss data just because of how data warehousing works.
Right. So the data warehouse might have these daily aggregates or something, and you need to say, tell me the number of times a user has tried to use this credit card in the past 5 minutes from point X in time.
Yeah.
That kind of thing?
Yeah, but it's aggregated daily, so if you try to do it yourself, if you have daily aggregates, you're never going to be quite right.
Right.
And the other really big feature is that Zipline gives you this same data streaming for free. So once you've backfilled your model and you want to actually use this in production, when you have real data flowing in, you can actually get that same data feed in the same exact format streaming. And it'll guarantee that streaming data more or less will match exactly what you would get at the end of the day, just using Zipline offline. So users don't really have to duplicate any of this work. And for many models, they end up being hosted both online, so in production using the website, and offline for analysis. So it's a pretty nice thing to be able to use.
And so the second kind of big category beyond the point-in-time correctness is what?
Users write a lot of boilerplate, a lot of boilerplate code in general. Like I said, data is rarely exactly in the format that you need. And there's oftentimes a lot of pre-processing that's done. For images, it's usually not too bad. It might be an impact on performance, but there's usually not too much code. But if you're dealing with text, you have to strip a lot of punctuation out, encode the text a certain way. Sometimes there's aggregation of features, like you might do, if this feature exists and this one doesn't, then I want to omit both or something like that. There's a lot of business logic that people encode as a result. And historically, we just saw that this was copied and pasted. Basically, you might have, 500 lines of copied and pasted code with tweaks.
Right.
So you can't just always copy and paste it and expect it to work.
Okay.
This became a really big problem because people can't share this stuff. They can't compose it very easily for a new model, and it's very, very error prone. So instead, we really focused on modularizing this. So we have a scikit-learn-like interface where people can wrap these unique operations that they can define or they can use our built-ins and compose them to build the entire workflow of the model. And then if they want to share just one piece of that with their teammates can use that chunk as the basis for another model. And this reusability was a pretty big bet, but it's something that we found was a huge win for many of our users. And it enables us to do these nice things like, at the end of my model, I'm using XGBoost, but I want to use now like a convolutional neural network. And in one line of code, I can just swap it out and it works.
Okay. And so where does this manifest itself in the system? Is this the feature store aspect of
this is a library that the user uses.
The Big Head library?
Yeah.
Okay.
Yeah. So if they're working in Python, they just import our library and can start just writing a model using the Big Head libraries.
Okay.
And if they want to use a TensorFlow model, like we have Keras and TF estimators built in. And then they can just use their normal TensorFlow syntax to build out their model. But it now cleanly plugs into the rest of their workflow. And so at the very end, they end up with a pipeline, basically just an object that contains all of their logic. And they can just save this thing, and it'll include everything they need to run it. And we run it verbatim in production. So,
okay.
Does
that tie into, do you run it via Graph and Airflow and that as the orchestrator, or how do you...
it has its own graph scheduler internally. So this will run on a single machine.
Okay.
So it'll execute its components, possibly on multiple threads. There's schedulers for different steps they might take, but it's meant to be real time. So, the latency is sub-millisecond in many cases for using this thing. Okay. Whereas Airflow might be for huge, backfill jobs.
Right.
So this entire graph, will run in online inference as well. So every time you submit a request, it's running through the whole graph. And in the future, there's plans to add components where we can have steps run on different machines and use remote GPUs and things like that. But for now, we found that even on a single machine, it's sufficient.
Okay. Okay. So those two pieces then summarizing are effectively kind of managing the data and figuring out how to deal with some of these trickier issues like point-in-time correctness and efficient backfills and things like that. And kind of, I guess I'll summarize as like raising the level of abstraction maybe so that the user has to write less boilerplate and can compose pipelines from things that are already provided for them.
Yeah, and also whatever they choose to write.
Right.
I think composability of their own code is something that we really care about as well. Especially if you're just hacking something out in a couple of hours. Typically, it's not going to be the nicest code, so at least encapsulating it, right?
Yeah.
Is a pretty good way to guarantee you can use that in the future.
Okay.
So, yeah.
Okay, cool. Yeah. So have you started looking at the TensorFlow 2.0 and like how that impacts the way, some of the things you've already built and the way that your users will be using TensorFlow in the future?
Yeah, it makes our lives a lot easier.
How so?
One of the key things they did in 2.0 is deprecate a lot of really old APIs. I think that was an issue we ran into where there was a lot of incompatibility within the 1.x releases. Certain APIs would only work with certain features, and that proved to be a really big source of frustration. I think by removing those old APIs and really focusing on kind of starting more of a clean slate, it means that developers using TensorFlow will usually, I would expect, have an easier time. And I think there's some other neat features in there as well. I think the fact they've moved to mostly eager mode by default is something that people would like to be able to use.
Do you find most of your users prefer eager mode to kind of the Estimators layers API?
The users that care about eager mode has historically been using PyTorch. Just because by design, it kind of works in that way. But I think they would consider TensorFlow as an option now that eager mode kind of works in a more easy fashion, and they don't have these other sort of static graph complexities to deal with for the most part. So yeah, I think it's going to emerge as a pretty viable option for many users just looking to prototype. Even in Jupyter, it's really nice to just be able to run a couple of cells and get a result.
Right.
So yeah, I think it's really opened up those features to people that I think would have not considered them in the past because of just the difficulty of using them.
They've done a lot around 2.0 and recently with integration with Colab and Jupyter Notebooks. Your team has built quite a bit of infrastructure around notebooks. Like, how do you see those playing together?
Yeah, I mean, they're very much two different approaches. I think I can't blame them, but Google does want to integrate with their own offerings. And we generally try to be really, really agnostic about what you're using. So while integrating with their own, they have this really nice Jupyter collaborative editor.
Google
Used via Google Cloud, yeah. But I think if users can leverage that, I mean, it's a great product. I've tried it out myself, and I'm sure it's a great option.
Do any of the new capabilities allow you to do more or better things in your own notebook implementation, or were you already doing everything you needed to do anyway?
We definitely weren't doing everything we needed. We have a long list of features that people like. One of the things I saw in the demo were just the ability to better show these TensorFlow graphs and kind of expose parts of your model inside a Jupyter notebook. I think that would be useful for us. But I would need to take a closer look at what that offering entails. So, I mean, anything they can do to better surface visualizations, I think that's one area where generally users are very happy if you give them better ways to sort of see what's happening under the hood. TensorBoard was one really, I think it was basically the only mainstream option that you could kind of do for visualizing models. And there just wasn't a very good way to integrate that nicely with Jupyter. There was a lot of caveats. So I think it'll be really exciting if they start making that first class and see what they do.
And you use within Big Head TensorBoard pretty extensively, right?
I wouldn't say
Am I remembering that correctly?
But
Or do you have your own visualization stuff?
we support TensorBoard. Not super well right now. But it's on a roadmap. There's a lot of internal visualizations that we have. We have our own visualization library for data and visualizing these pipelines. And we generally like to have a cohesive look whenever possible. So we'll probably continue to use that. But if a model exposes its own visualizations, we want to just leverage that out of the box. We don't want to, reinvent the wheel or anything. So as an example, one thing we did, XGBoost has feature importance kind of really nicely built in, and we can just expose that plot, and people have loved using that. So yeah, I mean, using TensorBoard or whatever the framework builds in is something that we, going forward, want to use.
And do you use any of the other kind of components of the TensorFlow, the evolving TensorFlow family, like the probabilistic programming or TFX or any of those other components?
Yeah, I mean, we would like to be able to use more of the components, but essentially how we operate is also largely based on what our users need the most right now. And there are other focuses at the moment, but I think as we plan on going and open sourcing this, it's going to be easier for other people to add support for these different features that they need. Yeah, probabilistic programming, there are a couple of frameworks that are kind of looking into this. I think Uber released one as well. Yeah, Pyro. That'd be really cool to add, but we just haven't had any tangible use case that immediately needed it right now.
It sounds like your focus is on enabling kind of the core use cases, and you haven't had much of a need yet to support some of these other ones.
Yeah, I mean, that's the kind of thing that I think if we offered it, you would find use cases for it. But yeah, you have to start somewhere. And I think giving users really, really good fundamental building blocks that work first are a good area where we can do that. I think estimators in TensorFlow are one area where they're really investing heavily in that, and we'd like to, have that also be really, really well supported as well.
And it's not currently?
We support some really basic use cases with estimators, so they have some pre-built ones, and you can define your own custom estimator.
Maybe take a second to explain what those are and how they're used.
Yeah, so estimators are basically TensorFlow's, I think, approach to something that's scikit-learn-like. We have a very, very simple API, essentially train and run inference, and the model is very encapsulated, right? You don't have to worry about sessions and graphs and all of these things. You basically define the structure of your model and what its input data looks like, and then you have something you can just play with, right? They provide a lot of built-ins, so like deep neural networks, you can kind of choose what those look like, linear models, and I think they have a couple of other ones as well that I'm not mentioning. And you can also write your own, so you can also just take TensorFlow code and kind of wrap it in one of these estimators. This fits really nicely with what we're doing in Big Head, where we're trying to encapsulate these models. So being able to allow users to use these more easily and not have to worry about anything other than the actual design of the model, that would be beneficial for them. So like I mentioned before, worrying about GPUs or where things are run, that's one question that we don't want our users thinking about. Just because we can almost always make more informed decisions at runtime about what that should look like. So they can get the best performance out of their models. So yeah, that's something I'm pretty excited to see what they do with. I think it was already in a pretty nice state not too long ago, but now that they clean up TensorFlow more in 2.0, it's probably going to be the de facto choice for a lot of people.
Any kind of taking a step back and kind of thinking about frameworks and the framework space from the perspective of someone who has to provide these to a set of users.
Yeah.
Do you have like a wish list or predictions or where you see it all going? Like, how do you see this evolving, or what would you want to see to better support your users?
Yeah, I think focus on developers and focus on the enterprise space is going to be one area that's pretty interesting. So, I mean, Google has been investing a lot in TFX, and it is TensorFlow specific. So, I mean, you do have to use TensorFlow. But it's also largely their attempt at handling the entire end-to-end, right? Data management, model management, all of this. We haven't seen that too much from other framework providers. But one thing we have seen outside of TensorFlow is a focus on modularity a lot. So another framework we've been exploring a lot is MXNet, and they've had a lot of focus as well on this. So I really see, I mean, you're probably going to have only a few big frameworks left after a while. For general use cases, it's just very, very hard to develop a new framework. So yeah, I mean, I see the main players still as probably TensorFlow and PyTorch and MXNet, with specific frameworks kind of lagging behind. I mean, you have things like Spacey and, you'll have things like Pyro for niche use cases or for NLP specific use cases. But yeah, I mean, a consolidation is very likely to happen. It's just not sustainable to have 10 of these and, developers splitting their time between them. But I think it's healthy to have competition. One example of that was PyTorch was kind of the first to have the ability to just run these computations on the fly, and TensorFlow then came out with eager mode, and MXNet came out with its own imperative API. So I think that's a really good back and forth that will really help everyone. I think there's been a lot of focus on the research space too historically. So making it really easy to do research is nice, but for most people, they generally have a rough idea of where they're going to start, and they want really nice higher level APIs. And then when they have those APIs, the other issue right now is usually when you use one of those things, there's such a performance hit that moving it to production is going to require more engineers. And that's something that we at Airbnb don't really have. I mean, we try to basically only have people writing models and maybe a team working on the infrastructure, but nobody actually dedicated purely to converting these models into a performant version, right?
Okay.
That's something that we think computers can do better. So,
Well, Alfredo, thanks so much for taking the time to chat with me.
thank you very much.
All right, everyone, that's our show for today. For more information on Alfredo or any of the topics we covered in this show, visit twimlai.com/talk/244. As always, thanks so much for listening, and catch you next time.